All right, here we are, 2.3, day number 2. Analytical techniques for computing limits when direct substitution doesn't work. Tools that we'll use are factor and cancel, clearing fractions, using conjugates. And then we're not going to touch on technology today, but we will in class a number of times. And then a little bit with limit laws, and I don't think we're going to get to squeeze theorem in this lesson, so we'll have to probably cover that elsewhere. So no squeeze theorem, but let's get started. So what happens when we try to evaluate this limit here, where f of x is x squared minus 2x minus 8 over x minus 4? Well, if you were to just go ahead and input 4 and see what this limit equaled, you'd get 0 over 0. So the first of our methods that we're going to use in order to help us here is to determine, do we have a hole here in this graph that's causing this disruption at x equals 4. So what you want to do is your first method, other than just evaluating by direct substitution, is to factor. So I'm going to look at this limit as x approaches 4. I'm going to factor the numerator, and typically the linear factor that you'll see in the denominator shows up in the numerator. So I'm going to go ahead and factor and make sure that this works. It looks like that would work, and then from there we're going to go ahead and do a cancellation. So we've factored and then we've canceled. This is method number 1. It should be your go-to if you ever get 0 over 0 as your evaluated limit. And now the function is just a line x plus 2. Now it's not just a line x plus 2, it's a line x plus 2 with a hole at x equals 4. Okay, so if I plug 4 into this, I get 6. So what that tells me is that the limit as x approaches 4 of x squared minus 2x minus 8 over x minus 4 actually approaches, from the left and the right approaches, y equals 6. Okay, let's look at our second method. Our second method, I'm going to expand here so I can read the whole thing. In example 2, says, let us look at another function, f of x, where we have x minus 1 over the square root of x minus 1 when x gets near 1. So the first thing that you want to just kind of investigate is what happens, right? What happens to this limit? Well, the limit as x approaches, what are we getting close to? 1 of this thing, x minus 1 over square root of x minus 1. If I do a direct input, that'd be 1 minus 1 over 1 minus 1, which is 0 over 0. That should ring a bell and say I got more work to do. So here we go. We're going to read the rest of this and see what we do. There's nothing particularly interesting anywhere other than where x equals 1. Our function is meaningless otherwise. We do not know what happens at x equals 1. However, we can look at what happens when x gets near 1. Alright, so we've done that. Okay, we get 0 over 0. So our next method is this thing called the conjugate. And what the conjugate is the conjugate of x plus 9 is x minus 9. Alright, these two are conjugates. And when we FOIL them, something cool happens. Outside and inside terms in FOIL, they cancel each other out. And then basically we've been able to simplify this expression and potentially do some cancellations along the way. So let's look at f of x. All right, let's look at the limit as x approaches 1 of x minus 1 over square root of x minus 1. Okay, we know this comes out to be 0 over 0, but what I'm going to do is wherever I see that radical sign, I'm going to figure out what its conjugate would be, which would be the square root of x plus 1. And I'm going to multiply the top and the bottom by that conjugate. And typically, you got your conjugate pairing on the bottom. It could be on the top. But what I'm going to do is I compute this limit and do some simplifying is I'm going to leave the top alone. I'm not going to change it at all. I'm going to leave it as x minus 1 and square root of x plus 1. I'm going to leave it alone. But in the bottom, I'm going to do some simplifying. So again, conjugates are great because they allow us to get rid of that outside-inside term, and we just have to do first times first and last times last. So square root of x times square root of x is x, and negative 1 times positive 1 is negative 1. And our conjugate method comes in handy here. So what this does is this turns it into a much simpler expression. Okay, I get that expression, and therefore when I do direct substitution now, which I'm allowed to do, okay, it looks like there was a hole in this graph at x equals 1. Okay, I'm able to do a direct substitution, and I get 1 plus 1, which means our limit would equal 2. Okay, again, 0 over 0 is an indicator we got more work to do. All right, our next method, clearing fractions. Again, first thing I would do is I would evaluate. I'd plug in a 4, so I'd get 4/5 minus 4/5 over 4 minus 4. Again, as you know, I mean, that's the goal of today, is to recognize 0 over 0 means more work to do. So I'm going to take this limit as x approaches 4, which is x over x plus 1 minus 4 over 5 all over x minus 4. And in this case, I'm going to do this method called clear the fraction. Okay, and I see the fractions in the numerator. I want to clear them out. So what that means, what I'm going to do is I'm going to get rid of the 5, and I'm going to get rid of that x plus 1 by multiplying top and bottom times this expression, 5 times the quantity x plus 1. All right, so let's see what we get. This comes out to be the limit as x approaches 4 of, let's see here, when I multiply the first term by 5 times the quantity x plus 1, I'll get 5x. The x plus 1s will cancel. And the second one, the 5s will cancel, so I'll get 4 times the quantity x plus 1. In the denominator, like I did before, because I'm doing a majority of my simplifying in the numerator, I'm just going to leave this as is, and I'm going to drag that 5 out in front. Okay, from here I'm going to do a little bit more simplifying. This will be the limit as x approaches 4 of, this will be 4x minus 4. So what I'll get is x minus 4 on the top, and conveniently that will cancel with the x minus 4 on the bottom. So when those go away, I'll get a 1 in the numerator, and I'll get a 5 times the quantity x plus 1 in the denominator. So I'm going to go ahead and evaluate this, plugging in x equals 4. And it looks like I get 1/25. Okay, let's keep moving. The last thing I want to talk about, and I'm not going to use any technology right now because I don't have that capability, is that this is a limit you just need to memorize. Okay, this limit right here is one that shows up many, many times. The limit as x approaches 0 of sine of x over x is a limit that we want to just know equals 1. That's something you need to memorize. And the other limit you're going to want to be aware of and memorize is the limit as x approaches 0 of 1 minus cosine of x over x. That one equals 0. This is going to be foundational for limits when we get later on into derivatives and everything like that. We'll be using these in a very important way. So I'm not going to do the last example, so I believe that is it for, nope, I think I got one more slide. Here we go. Let's do one more. Okay, some limit laws. Okay, these are just basic limit laws. You can see number 1, the limit as x approaches a of f of x plus g of x is just the limit of f of x as x approaches a plus the limit as x approaches a for g of x. Same with differences. If I have a constant, like you'll see in number 3, I can pull that constant out in front, do the limit as x approaches a of f of x, and bring the constant out as a product, or as a scalar. Product, similar deal. Quotient, similar deal, provided that your limit in the denominator does not go to 0. Power rule, again, you can just pull that out, find the limit, and take it to that power. And then your fractional power rules, same deal. So if I know the following, practice using these. Why don't you go ahead and stop the video and then come back and check out the answers. Alright, so for our first example, I just used our our quotient rule and our addition rule. So I just took the limit as x approaches 3 of f of x, which is 2, and for g of x, which equaled 5, and for h of x, which equaled negative 3. And I use those rules to find a limit of negative 7/3. For the next one, I would just take the 3 out in front, multiply it by the limit as x approaches 3 of f of x, which is 2. Multiply that by the limit as x approaches 3 of g of x, which is 5. And then separately, I would subtract the limit as x approaches 3 of h of x, which is negative 3. And it looks like I get 10, 30, 30 minus a negative 3, which looks like 30 plus 3, which would be 33. Last of all, we'd take the limit as x approaches 3 of g of x, which we could write like this: the limit as x approaches 3 of g of x, and cube that. We know that the limit as x approaches 3 of g of x is 5, and when we cube that, we get 125. And that'll be it for today, folks. Properties of limits and a couple of methods on evaluating limits when just direct substitution isn't working out. Have a great day. See you next time.